I'm Professor Cheng-fu Chen, Mechanical Engineering, and today I'm going to give you a head up of the ES331 mechanics material, and also give a head up starting from the chapter 1. Mechanics material basically is to study the response of the material to different loading types. In the first half of our textbook, we're going to study the 4 different loading types. The first one is this. We call the axial loading. And this is the major focus of chapter 2. The second one is we consider material model is a shaft, and the shaft is under torsions, T. And sometimes we mean the torsion means twisting or torque, and that is the topic chapter 3. And the third one we consider this is a beam model and under pure bending. So this is the chapter 4, and so here this is called the shaft, and this called bar. And here we use in solid mechanics we use in the different terminologies, the spatial communication tools to communicate with people what kind of the loading we kind of dealing with. So for axial loading we call material is bar, and shaft for torsion, beam for the pure bending. The last one is something like this. We consider a beam, and that is not under any type of this. It could be under this vertical loading, and the vertical loading can be anywhere, and even that can be under we call it distributed loading. And so this is F1, this is F2. For this case, inside here we expect the multiple types of the response will appear, and in particular we can analyze the loading types is we call the transverse loading. And this one in terms of our new version of our textbook, and that should be in chapter 6. So that is the first half of the mechanics materials. So starting from here, we really want to know how to quantify the response of the material. Basically, the response of the material to loadings. Usually we describe it as using stress or using strain. And here I just write it up the symbols we use in our textbook, and later I will give you the details for each one. So when we study the response of each material model to the loading, usually we focus on is we calculate, we concerned about what is the stress, what is the strain of the certain material to a certain type of loading, and that is the major focus of this class. And now while I'm erasing the board, and I'm going to jump into the chapter 1. And chapter 1 is an introduction to the overall the scope, but more specific in chapter 1 we're going to introduce more definitions about the stress. And here the stress has 2 kinds. Depends on the application of the loadings, we can classify like this. So now in chapter 1, we introduce the definition of the stress. Basically, stress by definition is the force divided by area. And so, for example, if you are using the unit, say newtons for force, and say if you use the meter square for area, then basically here is we define as the PA, called the Pascal. PASCALE. And most of time, and we have the scale and million of these scale. So basically, it's we call the MPa. M means the 1 billion, 1 million. And sometimes we can use the 10 to the 9th. So this one we call the GPa and gigapascal. So those are the units for stress. And the type of the stress. Here we classify into normal stress. And the second one we define as called the shearing stress. The difference between the normal and shearing stress is this. For example, if this is a certain structure, and here, for example, if you're interested in this particular cross section, and here I use dashed line to indicate the cross section here. So here, for example, if we have a loading, which loading is normal to the sections we're interested, then we call this as force. It's called the normal loading. And normal loading will induce the averaged normal stress. So we simply, for example, let me say this cross-section area equal to A, then the normal stress we call the average normal stress basically equal to F divided by area A. The second type is the shearing stress. So for example, consider again, we have structures, and then in particular, we are interested in this cross section. At this moment, we consider shearing stress in this direction. And now you can tell this force is parallel to this cross section. So in terms of calculation, this is called the shearing force. And in terms of calculation, we're using tau as the shearing stress, and by definition, and that is the force divided by the cross-sectional area, and again, this has the area A here. And this one will induce the average shearing stress, which is parallel to these cross-sections in particular. Okay, so now here, and that is the definition for the normal stress and for the shearing stress. So here we come up with the definition of the two terms here. And again, one more time, how to tell the difference between the normal stress and shearing stress. Basically, you decide it by the direction of the loading to the particular cross-section you're interested. So here come up with the definition of the stress. And with this in mind, then we can come up with further applications for how to use the fundamental definition and to analyze the more practical loading examples here. So here, let me use one simple example to demonstrate, and then in details we can go to see the slides later on. So here, let me make up one example here. So consider if we consider a material model, and for simplicity, we consider this is rectangle and has a uniform cross section. For example, is the same. So for this one, we consider this is under certain type of the loading. For simplicity, again, we consider this is under the axial loading, and the magnitude is equal to F. And now, for example, now we're interested in finding the stress in these sections. And now you can see this section is selected inclined. It's not vertical. So here we take the free body diagram. So this is called the free body diagram. And this is from your class statics, and you should have gained the knowledge about this one. So using the free body diagram, this is the loadings we applied from here. So let me repeat it here. In these cross sections, due to action, reaction, and due to static equilibrium, we expect they should have the loading here, that magnitude equal to F. And now to analyze further the distribution of the stress in this particular cross section, we simply is to decompose this loading into two components. One component is to normal to the sections. The other component is to be parallel to the sections. And here we decompose using the resulting the force theorem to do this one. Okay, so for example, if you really want to calculate, then we can see, for example, if say this is the angle theta here, so this is the angle theta here. So that means here this is the force component normal to this section, and this one can be calculated by F times cosine theta. And this component is the parallel to the cross section. So we can, in terms of calculation, this is the F times sine theta. Okay, so now we have the normal loading, we have a shear loading, so we can calculate per our definitions the normal stress equal to the normal loading, which is F cosine theta, divided by the area. So here for simplicity, let me say this inclined area is called A, so this is divided by A. And again, for the shear stress, that is obtained by dividing the shear force, which is F sine theta, and divided by the cross-sectional area A. So that's it. So this basically this step kind of lay out the general procedures of the more complicated practical examples. We take the free body diagram to expose the cross-section we're interested. We analyze the distribution of the external loading on that particular sections. Then we decompose that loadings into the normal components, shear components. We are able to calculate individual stress components here. So that is for the introductions. And in our textbook, chapter 1, we have very thorough examples to demonstrate this concept. And one final concept to deliver it in chapter 1 is called the factor of safety, and that would be the one here. The last topic we want to deliver is called the factor of safety, and we call it FS. The factor of the safety is this. In any materials, we under real testing, we gradually increase the magnitude F until this material is breaking up. Okay, so we increase the loading F. So in this way, in our experiments, we record the normal stress compared to deformations of this material. Then we can record certain curve. And at the maximum stress we can record it, we call it ultimate stress. And ultimate stress basically tell us the maximum capacity of the material can withhold the stress. And in terms of the real application of material, of course, we don't want to drive to the limit of the material. In practice, we want to give us a certain safety margin, not to push too hard to try to risk the failure of material. So basically, we define the factor of the safety is this. We give us designer will choose an arbitrary stress level we call the allowable stress. And here we call this, say, allowable. And this allowable stress is a number that arbitrarily chosen by designers of the system. So such that we calculate divide the ultimate stress by the allowable stress. and this one we define as the factor of the safety. So which means, say, if you choose the factor of safety equal to 1, which means you allow the system to have the stress, allowable stress equal to ultimate stress, and this is a very risk design. For example, if you choose a factor of safety equal to 10, which means you select your allowable stress is a 1/10 of this stress, which means, and at the most you can have your design only operate up to this and then. So this is a very conservative design, and so by choosing this one, either you choose factor of the safety or you choose the allowable stress in a way to allow your system to get certain the margins for not to risk the failure of the structures. So this is the exercise of the chapter 1, and from here we introduce the definition of the stress. We exercise how to use the free body diagram, and which is from your statics, and to analyze the fundamental stress, and that is the major topics of chapter 1. Thank you.